Hi, myself Dr. S.K. Bushra, former HOD, Department of Physics, Cotton University. This is a video lecture in physics for class 12 students. Lesson 1 of chapter 3, Electric Current. In this lesson, we'll consider moving charges and electric currents in conductors, current density, and finally, drift speed of free electrons. Let's begin. Moving charges and electric currents. Charges in collective motion constitute an electric current. However, all moving charges do not necessarily constitute an electric current. An electric current is established through a surface only when there is a net flow of charge across that surface. Let us consider an example to illustrate the point. On account of their random motion, billions of free electrons of a metal wire pass through any hypothetical surface in the wire per second, but they do so in both directions. So, there is no net transfer of charge in the process, and hence we do not obtain any current out of the random motion of the free electrons. However, we may connect a battery to the two ends of the wire to regulate the flow of free electrons in one single direction and obtain a current in the wire in the process. Our daily life is closely associated with electric current. Electric currents flow in transmission lines, in domestic wirings, and in household appliances. These currents are carried by free electrons of metals. Ions of both types flow in the electrolytes of the rechargeable batteries. Electrons and positive ions flow in ionized gases in fluorescent bulbs. We come across electric currents in semiconductors where currents are carried by electrons as well as by fictitious positive particles called holes. Currents we usually encounter ranges from very large to very tiny. In the large end of the spectrum, there is lightning. Lightning is a giant electrostatic discharge between two clouds or between the cloud and the ground. In the other extreme, there are those tiny nerve currents that regulate our body movements. In the figure, we have shown myelinated and unmyelinated neurons, which propagate action potential. Beyond the periphery of our daily life also, we come across electric currents. Two giant bands of radiation, known as the Van Allen belts, surround the Earth. Additional belts may also be temporarily created. In the figure, the radiation is shown in yellow, with the green representing the spaces between the belts. What happens in Van Allen belts? Energetic charged particles, most of which arrive from the solar wind and are captured in the belts, oscillate between the Earth's magnetic poles above the atmosphere. The photo credit is for NASA, Van Allen probes, Goddard Space Flight Center. Streams of electrons, protons, and ions fly out from the upper atmosphere of the sun. They are referred to as solar wind. High energy protons and atomic nuclei continuously travel through our Milky Way galaxy. They are known as the cosmic rays. Cosmic rays hit the Earth too. This is a photograph of Victor Franz Hess, who discovered cosmic rays in the year 1912. Electric current in conductors. From now onwards, we'll be focusing on steady currents of free electrons in conductors. We have already learned about the free or conduction electrons of metals. Please refer to Lesson 2, Chapter 1. Let us consider an isolated metallic loop. There is no electric field in the loop, and hence there is no current. Now we connect a battery as shown. The battery imposes an electric field inside the loop. The electric field exerts forces on the free electrons and urges them to move collectively. Thus, a current is established in the loop, which attains a steady state value after a very short time. Let A dash be a hypothetical plane that passes completely through the current carrying conductor. If charge delta Q passes through this plane in time delta T, then the current through the plane is I equal to limit delta T tending to 0, delta Q by delta T equal to dQ by dt. Suppose the conductor is of unequal cross-section. We consider planes AA dash, BB dash, and CC dash through the conductor as shown. Under steady state condition, the current I through all these planes is the same. Thus, the current is independent of the location and orientation of the hypothetical planes through the conductor. This is because of the fact that charge is conserved. For every electron leaving the conductor at one end, another must enter at the other end. The directions of electric currents. Although the current is carried by free electrons, the current arrows have been drawn in the direction opposite to that of the electron motion. The assumed direction of the current is a historical convention of current electricity. People learned about electricity much before the discovery of electrons. At that time, it was believed that the current was carried by positive charge carriers, and naturally, the current was assumed to flow in the direction in which positive charge carriers would move. But even after the discovery of electrons and knowing them to be the actual charge carriers in a conductor, the already well-established convention was not amended. Electric current is a scalar. Electric current is defined in terms of two scalar quantities, that is charge and time. Hence, electric current is a scalar. But usually one represents an electric current with an arrow. The arrow shows the direction of positive charge flow. These arrows, however, are not vectors as they do not follow the rules of vector addition. Let us illustrate the point with an example. Let us consider a current I splitting into I1 and I2 at a junction point. Conservation of charge dictates that I equal to I1 plus I2. Let us consider two different layouts as shown in figure 1 and in figure 2. The equation I equal to I1 plus I2 remains true in both the cases. Thus, current addition does not follow vector algebra. That is, I1 plus I2 is independent of the angle between I1 and I2. This confirms the scalar character of the current. The unit of electric current. The SI unit of electric current is ampere. 1 ampere is equal to 1 coulomb per second. 1 ampere is defined in terms of the magnetic force between two parallel currents. We will revisit the topic in a subsequent lecture. In the SI system, ampere is one of the fundamental units. It may be mentioned that the coulomb is defined in terms of the ampere. Electric current and potential difference. We may explain the electric current in the loop in terms of potential difference as well. In fact, we are more comfortable with the concept of the potential difference than with the electric field. We will learn later that the positive terminal of a battery exists at a higher potential with respect to its negative terminal. Therefore, when connected, the battery would establish a potential difference between the two ends of a conducting loop. Let V plus and V minus, plus and minus sign will be in subscripts, be the potential at the positive and the negative ends, A and B of the loop, when the battery is connected. Now, V plus is greater than V minus. The energy of the free electrons will be U plus equal to minus EV plus at A and U minus equal to minus EV minus at B. Clearly, U plus is less than U minus. Like any other physical system, the free electrons too are eager to minimize their energy. And they will do it by migrating from the high energy location B to the low energy location A along the loop, just like water flowing down a mountain slope. This mass transport of free electrons down the potential energy slope is the electric current. But as per the convention, we show the current in the opposite direction, that is from A to B along the loop. Now, why do the free electrons not take a shortcut through the battery? Because they cannot. Inside the battery, only ions can move. What happens after the electrons arrive at the lowest energy point in the conductor? The battery will maintain a steady current with a continuous supply of charge carriers at the expense of its chemical energy. We will revisit the topic when we will study batteries or electric cells. Current density. Current density is defined as the current per unit area through an element of a surface in a conductor. It is a vector quantity and is directed along the incumbent electric field. It is denoted by the letter capital J. The amount of current through an element of a surface in a conductor can therefore be expressed as dI equal to J dot dA. Here, dA is the area element whose direction is perpendicular to that element. Then the total current through the surface is given by I equal to integration J dot dA. If the current is uniform across the surface and parallel to dA, then J is also uniform and parallel to dA. Therefore, I equal to integration J dot dA. J will come out of the integration and we will get finally I equal to JA, or J equal to I by A. Here, A is the total area of the surface. Drift speed. The free electrons in metals behave like molecules of an enclosed gas. They move continually in random fashion at speeds of the order of 10 to the power 6 meter per second within the material. Their random motion, however, does not constitute a current, as it is not a collective motion in a particular direction. But the imposition of an electric field inside a conductor will cause the free electrons to accelerate in the direction opposite to the field. The free electrons begin to drift with a certain constant speed, called the drift speed. We'll revisit the topic in the next lesson. We'll denote the drift speed as V subscript D. We'll simply call it Vd. The drift speed is usually of the order of 10 to the power minus 4 meter per second. Drift speed and current density. The figure below shows a segment PQ of a cylindrical conductor of uniform cross-section A. An electric field E has been applied in the conductor in the direction QP. The electric field causes the free electrons of the conductor to drift together in the direction PQ. that is opposite to the field. The directions of the current and the current density have been shown in the figure. They are in the same direction as that of the electric field. We assume that all the free electrons move with the same drift speed Vd, and the current density J is also a constant. The number of free electrons in a length L of the wire is N into A into L, where N is the number density of the free electrons in the material of the wire. We have defined A as a cross-section of the cylinder in the previous slide. These electrons will cross the section Q of the wire in time delta t, say. Then delta t is equal to L by Vd. This is equation 1. And the total charge transported across the section Q in time delta t is Q equal to NAL multiplied by minus E equal to minus ENAL. This is equation 2. We know that the current is the rate of flow of charge across a cross-section of a conductor. Therefore, current I in the conductor is, using equations 1 and 2, I equal to Q by delta T equal to minus ENAL divided by L by Vd equal to minus NEVDA. This is equation 3. For a current which is uniform and perpendicular to the cross-section A of the wire, that is, for a current which is parallel to the vector cross-section A, we have J equal to I by A. Therefore, J equal to minus NEVD. This is equation 4. Equation 4 may be extended to vector form as J equal to minus NEVD equal to rho Vd. It is equation 5. The quantity rho equal to minus Ne is referred to as the carrier charge density, which is negative for the free electrons. For negative charge carriers, J and Vd point in mutually opposite directions. This brings us to the end of the lesson 1 of chapter 3. We will discuss resistance and resistivity in the next lesson. Acknowledgement. I acknowledge the book, Fundamentals of Physics, authored by Halliday, Resnick, and Walker, and published by John Wiley and Sons, Inc., for inspiration. Goodbye and thank you.